hello. We'll go ahead and get started. So this is the almost cloud-native deployment with AWS Fargate. I am James Alexander. The slides are already available. You can hit this QR code. I'll also splash it at the end so that you can link to it there as well. A little bit about me while you're getting the link for that if you want. I am James Alexander. I've been a C# developer for 10 years. And after I was a C# dev, I moved over to Python. And I'm currently in kind of a hybrid role of Python and cloud services over at Leaf Software. And we're going to talk about a project we worked on for one of our clients about kind of removing some tension and showing our client a new way of running their application in AWS. First, let's talk about what Fargate is. Fargate, if you search for it, you get a region in England. Has anyone ever been to Fargate, England? Yeah, you've been there. You don't have to tell me about it. It looks nice from Wikipedia. So there's apparently a market that they do 4 times a year. I mean, it's great, confectionery and all that stuff. Another type of Fargate is this guy, Go Gadget Technology.
We have successfully traveled eons across both space and time through the Fargate. To get free cable!
I think it's a Stargate.
It's the Fargate. F! It's different from that movie, which I've never seen. So how would I copy it?
Chill, man. It's all right. Let's just turn it on.
I just want to make sure that we are clear. It's the Fargate. Goes far, get it? And there is no way it came from that movie or that syndicated series based on the movie.
But it sure was a good movie.
Yeah, yes, it was. Turn on the TV. Maybe it's on.
Anyway, so enough of that. So what we're actually talking about is AWS Fargate here in this conversation. Anyone Aqua Teen Hunger Force fans out there besides me? No. Oh, hey, it's the same guy's been to England. Okay. So Fargate is really kind of this thin wrapper around the Elastic Container Service within inside of Amazon. So the key bullet point that you want to accept from Fargate is that you get containerized hosting, but you don't have to do any of your own hosting as well. So with standard ECS, you have to stand up an EC2 instance, your own virtual machine inside of AWS, and then you register an agent to the ECS service, and then that agent can run containers that you deploy to ECS. With Fargate, you remove your own EC2 instances. So instead, you're still just pushing containers up. You say, Fargate, here's my service, here's my task. Go and run it, and it hosts the EC2 instance behind the scenes, and so you get charged differently for that than you would if you have to pay for an EC2 instance and then the Fargate ECS costs. To talk about the organization of the project here. So this will kind of give you a little bit of background in terms of the story of why we did this in the first place. So Leaf is the consultant here. My team is the cloud services team. We're the one that call us DevOps, call us cloud architects if you want. There's also a group of developers at Leaf that wrote one of the projects for my customer. Under NDA, so I can't really tell you much details about them. I'm going to call them CapTech. At least I'm going to try and remember to call them CapTech instead of their actual name for this project, for this talk. But they are a investment software company. So your retirement accounts, your any type of IRAs and such managed by their software. And CapTech also has their own clients. So they can be both software vendors, they can be banks, they can be individuals that log into their website, check their retirement accounts, and summarize where their accounts are and balances and so forth. It's important to know from this structure that one of the underwriting goals here is that we had a lot of communication problems between the Leaf development team and the CapTech operations team. So a typical problem with DevOps that's trying to solve that communications problem. So we literally had occasions where the operations team and the developer team were saying the same thing, but talking past each other. Oh, and I guess we're going to move to the next slide. So that was one of our biggest roles and biggest changes, that we just had to tell them that they're actually saying the same thing and get them to talk together in a room together. Product one here is a legacy product that CapTech runs and Leaf software developers had written. It was a standard lift and shift application. It had been run on Expedient servers on Windows. And when they cloudified it, it was literally just running the exact same machines, the exact same configurations in AWS. One of the rules of DevOps that Calvin likes to talk about is not running EC2 instances like pets, and that's exactly what we have in this situation. What we wanted to move our client to was a product 2 scenario where there is more of a containerized deployment environment. We don't have to worry about maintaining specific logging or monitoring software on each of these EC2 instances. There's no manual logging in and checking on things. It's more of a, here's the operation as a whole, and individual containers, services can be deployed, taken down, and changed real time. So that was our goal for showing them how this is going to work. So there is no doubt in anyone's mind, including our cloud services team, that what we built here was way, way over-engineered for the problem we're trying to solve. But we wanted to show our client that there is a different way of hosting this application besides care and feeding of these EC2 instances. The existing app is that portal front end for the users to view their retirement accounts and their investments and so forth. It's running on a single IIS web server, SQL server. The web traffic is really low, less than 600 requests per day, so it's tiny. Think about how often do you really check your retirement accounts? A few times a year probably. So it's the same with our users. The biggest burden is this bulk file upload. And if you've been to Indy DevOps, we've given a talk similar on this same project, and most of these slides came from that talk. So I'll go into more about how we solve these types of problems. And so in the new environment, we're moving everything into AWS, but we're hosting it more natively. That is, putting it more into containers and not having any individual servers that we're maintaining. I go really quickly into a lot of these things. I breeze past a lot of AWS infrastructure and technology because I didn't really know who I was going to target for this type of talk. It's very technical, so if you have any questions, please throw them up on Slido. Mary Beth will wave at me and tell me that I need to answer the questions here. In terms of the application architecture, here's the overall structure. Like I said, CapTech users are going to be interfacing directly with the website. There are also developers, and these developers are going to be, say, banks or other front-end or API developers that are sending commands directly to an API or to FTP. The almost part of my almost title is that we're still using a single RDS instance. Actually, it's mirrored on different AZs, availability zones. So we do have a failover situation, but that is very much the bottleneck, as it's depicted in this diagram here. If I were to do this more cloud natively, I would say, we'd have to re-architect the way the data is stored and how queries are run so that we could store into, say, DynamoDB and then have a read store for queries and such. Given the needs of reporting users, they needed to have a queryable interface, and that's why we kept it on Postgres. Thanks to Entity Framework in .NET Core, we could have the CapTech developers write Entity Framework code, and it's agnostic to either SQL Server or Postgres. The overview of the file loading application is this type of linear structure. The arrows hide a lot of complexity, and we'll go into a lot of that detail in here in a minute. But the bottom line is that there's an FTP server. This is, again, one of the broken tenets of our DevOps rules in this project. There is a single purchased product from the AWS marketplace where you can say, host me an FTP server. And that's what the CapTech developer said. Here's an FTP server, and he just configured that to accept incoming FTP requests and dump it onto an S3 bucket. Our code and our infrastructure picks it up off the S3 bucket via an SNS message, triggers a separate Lambda, and goes into this tip function. So we'll talk about in just a second. To lay out the infrastructure, you have to first set up all of your infrastructure. We did this with CloudFormation, but not directly interfacing with the JSON. We use this DSL to wrap around it. So we get this thin layer of Ruby that we can define a hash table of here are all of our settings, here are some global variables, here's some security groups that we're going to need in lots of different places. The tool here is listed, and there are convenient commands. If you've already got a CloudFormation template, you can convert it into one of these Ruby scripts. I imagine it would look like any other generated code, but from there you can take it and parameterize certain global parameters if you want to. we created lines of CloudFormation templates around these bullets. So we set up a different template for S3, the network topology, and then the databases for disaster recovery. For DR, we use the US West 2 Oregon data center. So we'd have most of our resources in US East, and then replicated over to DR and in Oregon. Then separate CloudFormation templates for the cluster and an EC2 jump box. This jump box is really for anytime we wanted to allow the CapTech developers access via PostgreSQL. So we would give them an SSH shell into this, and then that would tunnel through to the backend database. So let's go into the details of our step function. Like I said, as a file gets dropped on S3, that triggers the SNS notification, and it starts into this step function. The problem with the way that files are going to come in is that they could be a thundering herd. Like all of these developers and all the banks could trigger the API at the exact same time. We're going to get 100 files dropped on us all at one time. The way AWS is going to trigger this is we're going to get potentially 100 different files all at once and 100 different step function instances triggering at the exact same time. So what get status and get already running checks for is it's trying to assert that there is exactly one step function running. And this is kind of a workaround. Or, there's better ways to do it today, and I'll talk about that in my last slide. But this is how we had to do it a year ago, because we didn't have queuing triggers based on SQS. So the way this works is that check if already running goes out and queries other step functions, finds the dates that they started, and compares it to its date. If you're the earliest one, you can carry on running. If not, you have to end, because you're not the one that's the winner that can process all of the files and loop over. And effectively, what we're doing here is we are throttling the number of files we're going to hit against our database. Since we have that single point of failure against our database, we want to not run 100 loaders all at once, because the instance size that we picked couldn't handle running 100 loaders at once. Based on testing, we threw a bunch at it, and the costing of where we wanted our RDS instance to be, we set it around 10, I think, for our starting number of loaders we wanted to run at a single time. If you've not used step functions before, they're really cool, and the dashboard here, as part of the console, is a really nice way of showing a business user how a workflow happens as part of the process. As you click on any one of these boxes here I'm clicking on get queue depth, you see the input and the output in its JSON form. So you can debug, if you've got a different workflow or whatever, you could see all the ins and outs, what they were at that particular time, and what they transformed to be after that Lambda function ran. Each of these boxes maps to a Lambda function that I wrote in C# code that runs and processes each step along the way. If you're a C# developer, you're used to serializing JSON with something like Newtonsoft or JSON.NET. Amazon provides their own library to do this. And at first I was like, I don't need Amazon's library, I've got my own thing. And it broke the passing of JSON into and out of C# functions. So once you stuck that Lambda back, the assembly tag back on there, you got your parameters serialized correctly. And these map exactly to that JSON object I just showed you. And that's the exact same parameter that maps into each one of these functions here. I've collapsed the code down for brevity, but this is the top level that maps to each one of those steps in the step function. The exception here on line 3 is the trigger. This is the code that runs immediately after a file hits the incoming S3 bucket. So the trigger here is to capture the event, capture what bucket and key was just dropped on, and add it to SQS. That's all that trigger does. Checking my notes to make sure I haven't missed anything here. The iLambda context interface here is another Amazon interface that provides, in my case, all I use it for is logging. So you get CloudWatch logs out of the box here. You just say context.logger, and then you can write to CloudWatch logs as part of your method call here. The get queue depth is going to tell me how many files I have stacked up behind my current position in the queue. So if I've got 100 files that dropped on, it'll be 100, and then it'll dequeue as I process files from start loaders. The interesting bit here is that if we have, say, 10 loaders that we can run at a time, we've already got, say, 5 of them running, but there's only, like, say, 3 files left in the queue, we want to run 3 more rather than trying to run 5 and failing on 2 of them. The actual starting of a task includes all the Fargate magic right here. Single line, launch type Fargate. There we go. We made it to Fargate. We'll see a little bit more, but there's really not much more to it other than a JSON structure that says, here's a task, here's a service. It's of type Fargate. And that specifies to run it in the Fargate infrastructure rather than having your own EC2 instances that specify where you're going to run this thing. We're using AWS Systems Manager to store environment variables. I'll talk a little bit more about that in just a second, but this defines are we in dev, test, or prod, and we get the cluster name and the task name. The task name will change because it includes the version number of the task. So as the logic for the business logic changes, we'll get a new task, and it'll have a new version pushed to it with each new update. My infrastructure background partner on my team knew instantly how to structure this command override such that, if you're familiar with passing in command line arguments, you're going to get an array of arguments to your command. So if you're trying to override your container command here, you need to specify a list of things you're going to pass to it. In this case, we're passing a script and then the bucket and the key that are going to be triggered and fired and run as part of the loader. We wrapped around the actual .NET execution. Here's our actual business logic that's going to run from our command line here. The issue we were running into is that the .NET command wasn't accepting a relative path. So we wanted to say, /command line / my namespace command line DLL. It was never finding the right command line to run. So that's why we wrapped everything in shell scripts to say, change directory to that first and then run the thing. envs on step line here, line 5 is a debugging step that just dumps our whole environment stack. So we know, did we make it to dev, did we make it to prod, whatever. And then the import argument here is part of the business logic that specifies, okay, our bucket and the key are going to be passed into that. Chamber is a tool that we use to automate and sit in front of the AWS Systems Manager to pull in environment variables. We'll see a little bit more of that later for the build process as well, but it's really nifty for packaging all that up and storing it all in one place within Amazon's parameter store. Deploying the lambdas is another shell script. So there's a .NET extension. So you say .NET Lambda Deploy, and then you give it the name and specify the assembly path for where the full path to the method name is. As I mentioned a couple times already, let's talk about Chamber. In a recent Indy Pi event, Josh Knox, wrote a brilliant project to add more cats to the internet. Because I think we all agree that there aren't enough cats on the internet today. And I'm not going to go just cats. We should put more dogs on the internet too. And Josh is talking today in Breakout A at 11:15. So you should go and see his talk after this. But one of the things that he mentioned in his talk was that as a speaker, we rarely say how we manage environment variables. We just say, we stuck an environment variable and pulled it out later, but we never talk about it. So let's talk about that. One of the top-level concepts that we use is this cross-account role assumption. So as a Leaf developer, we have an AWS development account, and CapTech has their own production account. So rather than creating roles and users and so forth in the production account for each Leaf user, we create a single role that mimics any Leaf developer. And then as we want to work on the CapTech account, we use a separate tool to assume a production account role from our development account. So Leaf developers only have developer accounts, but we can assume a role over in our production account. Then we can look at S3 buckets, we can interface with ECS tasks, we can do all of our work there from the command line or from other tools that we need to from there. This is all managed as part of the identity access management protocols within AWS. We use a tool called Assume that I've kind of mentioned here a couple of times. It's by Trek 10, and there's a Trek 10 speaker, I'm going to say Rob Ribeiro, that's speaking in Breakout B at 3:15 today. So giving you a lot of cross-promotion here for the conference that you're already at. But this is kind of how it works. You say Assume, and you give it the name of a profile. In our case, it's, say CapTech, and then you can do it as S3ls, and then you would see the list of buckets for that particular profile. This goes in your AWS config file. You've got your main profile for whatever your developer account is, and then you would have separate accounts for each other AWS account that you want to assume into. Chamber is a tool from Segment.io that we use to store most of our environment variables in. The only environment variable we don't is for our Bitbucket pipeline that stores the build user's key and secret. Everything else comes out of Chamber. So this automates the system parameter store within AWS. Because it's written in Go, it works on Mac and Windows and Linux. And you can specify a service, and we use these as separate build environments. So we'll say chamber write dev or chamber write test. Give it a name and a value, and you're off to the races on storing and retrieving parameters out of Chamber. You can also do bulk import and export with the export and import commands. You can specify JSON format. I think it accepts other formats as well. So this is how we work both locally and both from a build environment in terms of pulling parameters in and sticking them like in S3 or in Amazon. This is kind of a preview of the Chamber environment. I think most everyone can see it based on the height of this screen, but down here, this is our build script, and we run chamber exec, whatever environment we happen to be branched from, so either develop, test, or prod, or master here, and we specify the environment based on that branch, and then we can call the appropriate build script based on that step, and that environment will be passed along to it. The most dangerous part of this for me was writing the DR environment, because the DR only runs when we do a production deploy. And we do that so that as we update production code, we can also spin out Oregon instances for our new tasks, our new services, so that we have the latest task definitions in DR just as we deploy to production. But that means that if I make a change to the DR production script, I'm breaking the production build at the same time. Let's talk about ECS, the actual Fargate part. I mentioned before that standard ECS requires an agent. Here's a link to the open source tool that you would build on your own EC2 instances. The ECS agent then talks to AWS ECS to manage what containers it should run, what services it's going to run, what task it should run. And a task can be either a web task that's going to accept incoming requests or command line tasks that are going to be triggered on an event or on a schedule. The Fargate removes the requirement to run your own EC2 instances. Fargate manages the backend codes, and so it's now someone else's server that you're managing rather than having to run your own EC2 instances. That's unreadable, so let's go into here, and I'll dig into a little bit deeper. What we build from captext code is a container image that is the business logic and the code that's going to be run. We push that up to an Amazon ECR, their container registry. Could also be Docker Hub, depending on if your code is open source. Ours isn't, so we wanted Captech to be able to manage their own repository for their Docker containers. And then within their VPC, we specify these blue boxes for their task. I think that's kind of readable. But this is where all of the business logic now lives, within the Docker container, within a task that is specified by both a Captech developer and by the cloud services team at Leaf to specify what runs. In this case, it's the task that is triggered whenever a file gets dropped onto S3. Fargate here is this thin blue line that wraps around these that has its resources of managed EC2 instances that run all these tasks behind it. Similarly, you can have a service that the service definition describes what executable to run. And so now this is a web task, for example. So in our case, it's .NET and Kestrel. You could have Django running here. You could have Flask. You could have Ruby on Rails. The task doesn't really matter at that point as long as it's an executable that's going to accept incoming requests. There's a lot more examples here, Fargate task after Bitly that specify the JSON task definition that goes into a lot more detail. And I'll specify how we did it in our particular example here. Our build environment it's Bitbucket pipelines, I'll mention in a minute, but we really just wrap around shell scripts. And so a here document is going to just dump out a bunch of JSON. Due to the way that Chamber is going to inject parameters, we give it a string for what particular environment variables need to be replaced at the shell execution. Important bits here are the image. This is the actual environment that we're running from that gets specified above us from the build script. And we configure logging here to go to CloudWatch logs. And then the second part of the same script, this is our service that we're going to be executing. It's going to accept incoming requests. You can specify the CPU and task. You can go to a quarter of a CPU, and then memory can be up to 8 gigs and 1 gig increments. And you get charged proportionally based on how much you use in each of those cases. That's all for the task. Now for the service definition that specifies what task is going to run, you have to run a service within a cluster. And the cluster can be multiple tasks, as we saw in the previous overview. The task group ARN maps to the load balancer and the container that will be run as part of this. Specify your subnets, and then here again, all the magic within a single JSON property to tell it to run as Fargate rather than as your own ECS instance. As I mentioned a couple of times, we use Bitbucket pipelines so that as you push to master or any test branch, so if you say test slash release 1, release 2, you can have different test deployments based on that, all with Bitbucket pipelines. So with the pipeline's YAML structure, we give it a develop branch that just runs the build script to confirm that unit tests still pass, we can still do all of our deployments and push to a dev task environment. And then for each test branch and release branch, we just have a very analogous script that passes in release instead of a dev environment. We saw a little bit of this before, but the overview is when we check for what branch we're on, and we pass in the Bitbucket release tag. And the chamber magic happens down here to change that service in this case. So building an app is a lot of these stanzas over and over and over and over again. In our case, we've got 3 different tasks that we're running. We've got a web task, we've got an API task, we've got a CLI task. So it's really just this thing copied for each one of those things, at least in the cases where you have a service. So the API and a web service both have an update service. For just a task runner, you're just going to have a task that gets run here instead of the service part of it. The task definition ARN, it's the same script I showed you before that just does a here document of the actual JSON, and then we dump it out to here, and then we pass it into just the AWS CLI environment that's running in our Docker container. So we're using the Bitbucket Docker container to generate our task definitions, our services, and actually build Docker containers from within the Docker container. So it's Docker all the way down. A lot of this is pretty much straightforward copying assemblies and setting up startup scripts and so forth and so on, just to make sure that we get everything in our Docker container. And then we do a build on it, push it to the AWS repository, tag it appropriately with the right build version number and what environment it's going to be part of. And now it is over in ECS and ready for Fargate to consume. So in conclusion, since we've deployed this out, the same software engineers have used the exact same pattern on other projects. So I feel like we had some measure of success in showing them that there is a brave new world of deploying apps rather than just a standard EC2 instance with IIS and so forth running on it. For the most part, he got all the structure set up exactly as it needed to be. Given that he's not a cloud architect, he was able to copy and paste the same structure, and he got tripped up on configuring security groups and a minor networking infrastructure like that. But other than that, he got it configured all on his own. The most recent commit we made on this was June 6, 2018, and then June 28th, AWS announced SQS triggers for Lambdas, which would have removed any of our need for step functions. So a good portion of the code we wrote would go away because we could just now trigger on SQS Lambdas instead of having to write our step function logic and have all that built in and wrapped around. As of this January, Fargate announced a price drop. So it is now less expensive to run Fargate with this configuration than it is to run the least expensive EC2 instance. So based on the numbers that I found earlier today, or earlier when I wrote these slides up. You can find more of me at jamesralexander.com. I don't have a blog post posted with these links yet, with these slides up yet, but the link is there. I'll be around at the conference if you have additional questions. Other than that, thank you very much.